In our journey to make sense of the universe, the subjects that provide us with references seek answers to the most important question humanity has ever asked, especially when it comes to physics. Why are we here, and what is reality? Mathematics, on the other hand, is simply a language we use to describe the physical forces, atoms, dimensions, and energy that underlie all sciences. A tool. So when we say physics, we usually think of the cosmos, distant planets, galaxies, neutron stars, and so on. That's not it. Physics is actually the foundation of all sciences. Chemistry, for example, it essentially studies the interaction between atoms, and it is physics that fundamentally seeks to understand this relationship. Think about yourself, your body, all your organs, your brain, and even your consciousness, when you get down to their essence, can be described in terms of chemistry and physics. So even biology is fundamentally based on chemistry and therefore physics. It can also be expressed through mathematics. Mathematics is actually a field that everyone, whether educated or not, should know in some way, or at least understand at a basic level, because mathematics is the language we use to make sense of and describe the universe through physics in our quest for meaning. The language of the universe is mathematics. Physics, on the other hand, is the world's most enjoyable field of study, examining all the laws of the universe, including chemistry, leading us to the truly important answers and raising many more questions in the process. That's why, in line with the purpose of So Far Science, I want us to embark on a journey through physics. Let's start a series that will continue for a long time. There will definitely be other topics in between, and our search for meaning will always continue within this framework. Ultimately, we will embark on a journey that leads to theories such as superstring theory and similar theories, which are claimed to be the theory of everything that scientists like Einstein pursued and tried to discover throughout their lives. So, shall we begin? When it comes to physics, you will hear the names Newton and Einstein frequently throughout this series. We will also mention many other physicists, and of course, we must talk about the famous apple. This event, which has always been a source of humor and jokes, was actually just one of the examples Newton used to explain gravity. According to records, when explaining gravitational pull to his friends, he said that the apple falls in a straight line toward the Earth's surface because a force is applied, and this force is definitely centered on the Earth. So the apple didn't fall on his head. We get caught up in this anecdote and miss the real point. Newton had already spent a large part of his life trying to understand the motion of the planets, particularly the moon's orbit around the Earth, and, in keeping with the true purpose of science, he wanted to understand what Aristotle and Galileo had said, and, most importantly, explain it simply. Simplifying is exactly that, and the laws of motion he developed would still be used 350 years later in calculating the orbits of rockets sent into space today. And when he developed the laws of motion in 1666, he was only 23 years old. He would explain all these laws 28 years later in 1687 in his book known as Principia. Its other name is Philosophia Naturalis Principia Mathematica. The reason Newton waited 22 years before writing this book was of course the reactions to the laws he claimed and financial constraints. However, with the persuasion and financial support of Edmund Halley, the discoverer of Halley's Comet, he wrote this book in 3 volumes in 18 months without pause. Yet, very few people had the privilege of reading this book. Even if many physicists read it today, they would not understand much. This is because when Newton wrote this book, the mathematics he needed, namely calculus, had not yet been discovered. Calculus is the most important stage of mathematical analysis, which has sub-branches such as differential, integral, and derivatives. It is used in every model involving motion and variables. In other words, it is used in every area of life without exception. For example, it is used in fields where mathematical modeling is required and the most appropriate solution tests are desired, primarily in natural sciences, computer science, statistics, engineering, economics, business, and medicine. And Newton, while explaining the laws of motion, was forced to discover calculus in a way. Newton is also the one who discovered this subject, which is taught to all engineering and science students in their first years. For this reason, and others I will explain shortly, this book is considered perhaps the most important work in history, alongside Aristotle's Metaphysics, Plato's Republic, and Darwin's On the Origin of Species. So why is this book so important? What is its subject? What does it say? In this book, Newton explains his famous laws of motion, Newton's first, second, and third laws of motion. You've probably heard of them. If you've ever taken a physics class or read about it somewhere, you've definitely come across them. But what do these laws mean beyond their magical formulas? What do they govern? Actually, almost everything that shaped the 20th century. These laws form the basis of classical mechanics. To put it simply, Newton's first law of motion states that unless acted upon by a net external force, an object at rest will remain at rest, and an object in motion will continue to move at a constant speed. Now, that's the definition, but what does it mean? First of all, for thousands of years before Newton, Descartes, and Galileo came up with these laws in the 1600s, all scientists thought that an object tended to come to rest. So when you throw a ball, they said the ball will inevitably tend to come to rest, independent of everything else, and eventually will stop. So when Newton states in his first law of motion that an object will maintain its state of rest or constant motion unless acted upon by an unbalanced external force, he means that if you throw that ball and do not apply a counteracting force, i.e. a force equivalent to the ball's mass and momentum, it will literally continue to move at a constant speed forever. Now, this may seem a little strange to us. In everyday life, we know that if we don't touch a rock, it will stay there for thousands of years. Okay, no problem there. But what does it mean to say it will go at a constant speed forever? This is not something we can experience under worldly conditions, because when you throw a ball, air resistance and friction after it hits the ground cause the deceleration we mentioned and ultimately produce a counteracting force that causes the ball to stop. For it to continue forever, there must be no force at all. No friction, no air resistance. Where can we see this? In outer space, of course. How do you think people who experience the world like we do arrived at this conclusion? By observing the planets, of course. While researching how the Moon, Earth, and other planets maintain their motion. In other words, as the Earth revolves around the Sun, it maintains its constant speed and continues its motion indefinitely. The reason the orbit is elliptical is the gravitational pull of the Sun. It only exerts enough force on the Earth to change its direction. Actually, the best example of the first law of motion is this. Imagine you are on an airplane. The plane is in the air and traveling at 800 kilometers per hour. But suppose the plane has no windows. You cannot see outside. Also, your headphones are on and you don't hear any engine noise. There is no turbulence or anything else. In this situation, is it possible for you to tell whether the plane is moving or stationary? No. Okay, we understand. An object remains stationary or maintains its constant speed as long as no net force is applied to it. That's clear. But what happens when a net force is applied to this stationary or constant speed object? How does this force affect the object? This opens the door to Newton's second law of motion. We mustn't think of the second law as unrelated to the first law. The first law talks about inertia, that is, maintaining its state as long as there is no force. The second law talks about the force needed to change this inertia, and it presents us with this very famous formula, F equals m times a. Here, F is force, m is mass, and a is acceleration. Before giving an example, let's also mention that mass and weight are different things. Mass is the amount of matter a substance has. Weight is simply the expression of the gravitational force applied to the substance. This law, also known as the law of acceleration, states the following in short. When a net force is applied to an object, acceleration occurs. The greater the force applied, the greater the acceleration. The greater the mass of an object, the lower its acceleration will be. For example, suppose you have two cars, one weighing 1 ton and the other weighing 2 tons. Both have 150 horsepower. The reason the 1-ton car accelerates from 0 to 100 twice as fast as the second car is because their masses are different. In short, force is directly proportional to acceleration, and mass is inversely proportional to acceleration. Therefore, we can also write the formula F equals ma as A equals F divided by m, and we can find the unknown by using it as a variable. Now, when it comes to Newton's third law of motion, we encounter the definition that almost everyone uses in their daily life as an idiom: action and reaction. More scientifically, for every action, there is an equal and opposite reaction, always. As a brief side note here, we need to emphasize that we need more than one object to talk about a force. If we assume that an object in space is not subject to any gravitational force, then we cannot speak of a force in this case. In other words, force is not a concept that exists on its own. Anyway, the third law essentially states the following. For example, if you try to push a refrigerator, the refrigerator will try to push you back. What's the connection? Let's explain. In fact, let's have astronauts from the International Space Station show us. In this environment with microgravity where friction and air resistance are minimal, we clearly see that an astronaut pushing another astronaut encounters an equal and opposite reaction. This is precisely the third law. Of course, Newton didn't stop there. One of Newton's most famous discoveries is the universal law of gravitation, which I mentioned at the beginning and is associated with the Apple story. This law simply states that any two objects with mass attract each other. So, in the apple example, the Earth applied a gravitational force on the apple, and the apple applied a gravitational force on the Earth. But, of course, due to the mass difference, the Earth prevails. For thousands of years before Newton, everyone thought that objects simply fell to the ground on Earth and that the universe was organized accordingly.
Newton, starting from this simple example, proposed that planets also exert the same force on each other and formulated this, and by discovering that the force that causes an apple to fall to the ground is the same force that keeps the moon and the Earth in their places, in their orbits, he made the universe much more understandable. Just as science should, he unified and simplified it. But there was a problem. Yes, the law of gravity could calculate gravitational force with a very high degree of accuracy, but Newton had no idea how gravity worked. This question remained unanswered for almost 250 years, and no scientist dared to tackle the problem. Until 1905, a young man working in a patent office in Bern, Switzerland, whose name was unknown to anyone, would change everything. Who was this man? Albert Einstein. Let's leave it there for now. If we start talking about Einstein, we won't be able to stop. We'll cover the rest in the next video of this series. I hope you enjoyed it. And as always, thank you for being here. See you next time.